So this is our second example of calculating a mineral component or a set of mineral components when we're given a set of oxides that have been measured. And in this case, we're going to look at a feldspar. So let's say we have a feldspar where the SiO2 content is 64.66. Al2O3, I'm just going to rewrite it here, is 19.72. Let's say the calcium is 0.34 weight percent, Na2O is 3.42, and K2O is 11.72. So these are weight percent values that we would get from an electron microprobe or some kind of X-ray fluorescence spectrometer. That means that if we take the sum of this, and it should be a little bit less than 100, that sum should be very close to 100. If we had 100 grams, then about 65 of those grams would be SiO2, about 19.7 grams would be aluminum, etc. So how are we going to get the mineral components? The mineral components we're going to be interested in are things like anorthite, albite, and orthoclase. So what would be the proportions of those molecular quantities? Well, we're going to do the same thing that we did with olivine in another video. The first step here is to divide by the molecular weights. We'll just write that as MW, and here are the molecular weights here, all in grams per mole. But we're going to do something a little bit different. So with silica, we just have one silicon atom per SiO2 molecule, so we're going to divide that by 60.08. But for Al2O3, I just want to count aluminum atoms. And since there are 2 aluminum atoms for every molecule of Al2O3, that's twice the amount of aluminum I really need if I just want to count aluminum atoms. I want half this amount. So I'm not going to divide by 101.96. Instead, I'm going to divide by half that amount, which is about 50.98. For calcium oxide, I've just got one calcium per CaO molecule, so I can just use this, 56.08. But for sodium, Na2O gives me twice the number of sodium atoms that I really want. I just want to count individual sodium atoms, so I'm going to cut this in half, and we're going to divide Na2O by 61, not 61.98, but half that amount, 30.99. And then we're going to do the same thing with K2O. We've got 2 potassium atoms there, so I'll take half the amount of 94.2, which is 47.1. So what I have here are SiO2, but I don't have units of Al2O3. If I divide here, what I really have are units of AlO3 halves. I've still got calcium, but now I have NaO1 half and KO1 half. I don't have K2O or Na2O. I'm taking the molecular weights of things that only have one cation per oxide. And that's going to make our life a little bit easier at the end. So we have these molecular weights, and when we do those series of division problems, here are the numbers we get. For silicon, we would get 1.076. For aluminum, something close to 0.387, about 0.006 for calcium, 0.11 for sodium, and about 2.249 for potassium. And the sum of all those things is about 1.828. That's an odd sum to work with, so we will renormalize. So step 2, we are going to renormalize, which means we'll divide everything out by 1.828, divide by 1.828, not 822, etc. We'll divide all those out, and when we do that, we will get these values. We'll get 0.5884 for silicon, 0.21 for aluminum, 0.0033 for calcium, about 0.006 for sodium, and about 0.1361 for potassium. And if you carry out all the decimals in Excel, then this will come out to exactly 1. Now, we're going to erase the chalkboard here and just focus on these fellows here. And the reason why is if we're interested in anorthite, albite, and orthoclase, let's take a look at those compositions. So for albite, we have NaAlSi3O8. For orthoclase, KAlSi3O8. And then for anorthite, CaAl2Si2O8. So we've written these all on the basis of 8 oxygens. Notice that there's a lot of stuff going on. The cations, sodium, potassium, and calcium are all changing, but so are the aluminum and silicon proportions here, especially when we shift from the alkali to the anorthite containing feldspar. So we have to worry about this charge balance, but actually we do not. Since we can define the kind of plagioclase, or the kind of feldspar that we have based on sodium and potassium and calcium amounts only, we could focus just on those. So even though things are changing over here, we can focus on what's going on in this site that holds the sodium and potassium and calcium to decide the proportions of anorthite, albite, and orthoclase, because anything that contains potassium necessarily has an orthoclase component. Any feldspar that has sodium will have an albite component. Anything that has calcium must be an anorthite component. So since these atoms are particular to these kinds of feldspar components, we can just focus on those. And that means what we're going to do is we're going to just take the sum of CaO, NaO 1/2, and KO 1/2. And now you'll be able to see why we took just one cation of each of these. The sum of these three fellows here is about 0.199777 or so. So let's erase the chalkboard here. We're going to carry these numbers here over to our next chalkboard. So the anorthite component will be the amount of calcium relative to the total amount of calcium plus sodium plus potassium. And this is why we only wanted one cation each when we looked at those cation fractions. And so this would be equal to 0.0033 divided by 0.199. Let's just round it off to 998. And this is equal to about 0.02. For albite, that will be equal to about 0.06 divided by 0.1998, and that'll be equal to 0.3. And then for orthoclase, we'll take the amount of potassium oxide, 0.1361, divided by 0.1998, and that'll be about 0.68. So we have something that is 2% anorthite, about 30% albite, and 68% orthoclase. And all those things should sum to 1. So let's erase the chalkboard again. We'll look at how we would write that. We could write that as AN2, albite 30, and orthoclase 68 using subscripts to represent the molecular proportions of things that have an anorthite formula, an albite formula, and an orthoclase formula. So this is the way we would calculate a feldspar composition. And by the way, the mole proportions that we calculated, we could also call them cation fractions, cation proportions, or cation fractions. So this is the name that we use for mole fractions. So these are mole fractions when we talk about so-called cation fractions. These are mole fractions where all of the oxides that we list, such as SiO2 or aluminum, here AlO 3/2, etc., where everything has only one cation per formula unit. So we would write things like this. Instead of Al2O3, we'd have AlO 3/2. We just take Al2O3 and cut the whole thing in half. Similarly here, Na2O, cut the whole thing in half, and we have NaO 1/2. So cation fractions are mole fractions where we only have one cation per oxide that we're examining.